Okay. There are exceptions to the Aufbau principle. You don't really need to memorize them. You need to be aware of them, and you need to be able to explain why. And the explanation why is always it's a lower energy configuration, because the Aufbau principle holds true all the time. So when we're looking at period 4, here we have the transition metals. We start filling them, and when we get to krypton, really what should happen is that instead of, you notice one electron is missing here, I should have a pair of electrons there, and then 4 electrons here and 2 electrons there, but I don't have that. For krypton, what happens is I end up unpairing that one pair of electrons. Now you notice everything in the S and the D sublevel is unpaired. That is a lower energy configuration, so that's an exception. So the same thing happens with copper. You'll notice when we get down to copper, instead of having 2 electrons here and 9 electrons there, one of the electrons goes, now I have a full 3D sublevel and a single electron in the 4s. So again, this is a lower energy configuration than leaving the 2s electrons, the 2 4s electrons together in the 4s sublevel. So there are some exceptions, and the exceptions occur because it's a lower energy configuration, because these sublevels start getting closer and closer together in energy. And that's why when we get to Fs, there's so many exceptions, and it doesn't just fill straight Fs, because everything's so close together that the electrons don't just fill one sublevel before they fill another sublevel. Okay. So one of the advantages of using the noble gas configuration is it separates out the core electrons from the valence electrons. All of these electrons are inner. They're not in the outermost energy level. They're called core electrons. The 4s and the 4p, the 4 is the highest occupied principal energy level. So those electrons are your valence electrons. Those are the electrons involved in bonding. You notice we also have the Ds in there. Once the D sublevel fills, that usually is pretty stable energy-wise, so there isn't a lot happening, but sometimes you may end up using the D sublevel. But the 4s and the 4p are definitely always valence electrons. That S and P, outermost S and P, those are your valence electrons. So when we go to write electron configuration for ions, we simply add or remove electrons depending on whether we have a positive or a negative ion. So when we're forming negative ions, we have to add electrons to make it negative, and the number of electrons added pretty much fills up that whatever sublevel is partially filled. So an oxygen atom, neutral atom, has this electron configuration. Oops, that should be a superscript 2, 2s2. So that would be oxygen neutral atom. You notice 2p6, same as neon. Bromine, neutral bromine would be argon. 4s2, 3d10, 4p5. So by adding that one electron now, it has the same electron configuration as krypton. And this is kind of the basis of the octet rule, which we'll talk about when we talk about bonding. Okay. When positive ions are formed, that is, when a metal atom becomes a cation, the electrons are removed from the atom. That means they're removed from the electron configuration. Okay, the first electrons lost are those from the highest principal quantum number. That's the first thing to remember. So I look for the highest principal quantum number, take those electrons first. So if you end up having 2 subshells with the same principal quantum number, electrons are lost from the subshell with the higher L number. So electrons are lost from P sublevel before they're lost from the S sublevel, because remember the L number for P is 1, the L number for S is 0. So let's take a look at a couple of examples. Neutral fluorine, fluoride. Neutral sulfur, sulfide. So those ones are pretty easy. Now let's look at these. Strontium, which is in group 2. Hey, loses those two 5s electrons and becomes a positive 2 ion. Titanium, when it becomes a +4, loses these 4 outermost electrons, becomes a +4 ion. Now look what happens with iron. When iron forms a +2 ion, the 2 electrons to go are the two 4s electrons, because 4 is bigger than 3. That's the principal quantum number, that's your n number, that's an n number. Since 4 is bigger than 3, the s electrons leave first. Then the d electrons leave if I have higher than a +2 charge. So even though the d's filled last, it isn't last in, first out. It's higher principal quantum number leaves first. So if I'm looking at cobalt, so first I want the electron configuration for cobalt atom. Cobalt is number 27. So it's in group 9 and it's in row 4. So cobalt would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d, and that should be 7. Yes, that's 7. So that's cobalt atom. When cobalt forms a +3 ion, it's going to lose, let's see, these 2 electrons and 1 of those. So now the electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 3d6. So you notice the 4s electrons are now gone. And then I was asked for the noble gas configuration, so now that means I'm going to stop there. I'm not going to touch the 3d because the 3p is the noble gas at the end of row 3. 3d, remember, is in row 4. So the noble gas at the end of row 3 is argon. And then I have 3d6. So that would be the noble gas configuration for the cobalt 3+ ion. Okay. Last thing I want to touch on briefly is magnetic properties. Many metals exhibit magnetic properties. Some of them are temporary, some of them are permanent, and that depends on, in some respects, how electrons are arranged. So we have metals that are exhibit diamagnetism, or so they are diamagnetic. Hey, and what that means is that they have all paired electrons. There are no unpaired electrons. These metals do not exhibit magnetic properties. So diamagnetic elements have no magnetic properties. Paramagnetic elements that display paramagnetism, have induced magnetism. They have unpaired electrons. So what happens is these atoms are arranged randomly, so the unpaired electrons are not all pointing in the same direction. So some of them, as they go from atom to atom to atom, the electrons, the unpaired electrons, although within an atom they're pointing in the same direction, from one atom to another they may be pointing in different directions. So they tend to cancel each other out. However, when they're exposed to an electric field or a magnetic field, so I expose them to a field, all of a sudden, even though they're in different atoms, now all the unpaired electrons are lining up. And when they all line up, then that metal displays magnetic properties. So I can induce magnetic properties by exposing a metal to a magnet or to an electric current. And that's how you can make a magnet, is by exposing the piece of metal for an extended period of time to a magnetic or electric field. Then there's a third type of magnetism called ferromagnetism, which is what we associate with permanent magnets. So those are magnets. The thing that's sticking to your refrigerator is a permanent magnet. So that displays ferromagnetism. So, and that's an iron and a few other metals. Neodymium is a really strong ferromagnetic element, and that's the magnet that's used in computer hard drives. It's extremely strong. And so these magnetic properties are based, at least in part, on paired versus unpaired electrons in atoms.